Dear students, grade 12. Today's lesson we're going to continue about this chapter, which is equilibrium. In the previous video, we started talking about the indicators, and we said that indicators should be suitable to the type of titration, and we also have learned about the types of titration between strong acid, strong base, strong acid, weak base, strong base, weak acid, and weak acid and weak base. Also, I need to remind you that we said for each of these titrations, we have a suitable indicator. This is to revise the suitable indicators for each of these. For example, if the titration between strong acid and a strong base, we can use phenolphthalein or methyl orange, but it's preferred to use phenolphthalein because it has a clear color change, and this is one of the main points for the perfect or the suitable titration. It has to have a clear color change using only one drop. In titration between strong acid and a weak base, we can use methyl orange. In the titration between strong base and weak acid, again, the phenolphthalein. But in using weak acid and weak base, the titration between weak acid and weak base, actually neither methyl orange or phenolphthalein is suitable because it does not give a sharp change at the end point. And we said also one of the main points for the suitable indicator that it has to, there is an equal, or the end point should be equal to the equivalent point. And the equivalent point, as we have defined that, it's the point in which the color of the titration solution changes. But we also said that the titration curves, actually it shows the change in pH along the chemical reaction in the titration. When the acid and base are actually reacting, the pH also changes, and that's why there is the curve, the titration curve. Okay, so here's the question: what color is methyl orange in acid, and what color is it in an alkali, and what happened to the pH as they react? So methyl orange actually is red in acid, yellow in an alkali. Okay? Again, methyl orange is red in acid and yellow in alkali. So the change will be around, the change of the pH will be about from 4 to 5. Approximately same pKa value. Remember the pKa? The pKa is minus log the pH. That's why methyl orange is used when you're using, let's check here. See, when you're using strong acid. So methyl orange, that's why it's a suitable indicator for strong acid, and weak base. But when there is a question why it's the suitable indicator to use in the titration between strong acid and strong base, because actually the change of pH for this indicator will be from 4 to 5. 4 to 5, actually it's acidic. It's less than 7, so it's acidic. Now, what color is phenolphthalein in acid, and what color is it in an alkali, and the pH change? Actually, phenolphthalein is colorless in acid, and it's red in alkali. The change of the pH is from 9 to 10. That's why it can be used when you're using strong base plus weak acid, because the pH change is from 9 to 10. 9 to 10 is more than 7. This means that it will be shown clearly when it's more basic, when the solution is more basic, that strong base and weak acid. Now, what is a buffer solution? Also, we started that the previous video. A buffer solution actually is a solution that resists the change in pH when small amount of acid or alkali are added. So now we know that the buffer solution is a solution that resists the change in pH when you're using a small amount of acid or base. So there are two types of buffer solutions. There's acidic buffer solution and there's basic buffer solution. Now for the acidic buffer solution. How can you make a buffer solution which is acidic? Acidic buffer solution is made from a weak acid and soluble salt of that acid, which is fully dissociates. Okay? So again, a buffer solution, acidic buffer solution, is made from weak acid and a salt of that acid. Weak acid, soluble salt. Remember, soluble salt of that acid. That's why it's fully dissociating, means it's completely dissolved. Okay, so this is the equation of the reaction between acidic buffer added to acid. If you have an acidic buffer added to acid, so this means, we said, remember, that it resists the change of pH. So if you're having acidic buffer added to acid, this means that it's opposing the addition of hydrogen, means it's reacting to decrease the concentration of hydrogen, that because it's opposing the change of pH, right? Now, write the reaction between acidic buffer if it's added to alkali. Remember the pH. The pH is measuring the concentration of hydrogen. Okay? So, if buffer solution is resisting the change of pH, this means that it's decreasing or increasing according to the reaction. It's changing the concentration of hydrogen. Right? So for the first reaction was the acidic buffer reacting with acid. If it's reacting with acid, so it opposes addition of hydrogen. Opposes means it's against or resisting the addition of hydrogen. But what if you add the acidic buffer to an alkali? So if you're adding an acidic buffer, this is an acidic buffer. If you add it to alkali, it forms water. Okay? So what do basic buffer solution contain in general terms? So we identified acidic buffer, it's a weak acid added to its soluble solution, soluble salt. For basic buffer, it's a weak base and soluble salt of that weak base. Now, how can you calculate the pH of a buffer solution? Remember how we can calculate the pH of different solutions? We can calculate the pH, we've learned how to calculate the concentration of hydrogen, the concentration of the hydroxyl group, and the pKa, and we have learned what is the relation between the concentration of hydrogen and pH, and also the relation between the pKa and the concentration of hydrogen. Use the Ka to calculate the pH of the buffer solution. Actually, there are some steps. Okay, all you have to do is just learn these steps and learn how to use it. First, you use the Ka of weak acid. So in a weak acid, this is the concentration of the negative ion and the concentration of Ha. Then you can calculate the concentration of hydrogen and then the pH. Okay, now to calculate these, we will divide the steps into two methods. We have two methods. These are long calculations that use acid-base calculations, right? There are two types. If you have an acid and base, if the problem or the question is about the reaction between acid and base, these three steps actually you have to follow them just to determine the pH. So if the question is about acid and base, you find the number of moles of each species, the acid and base, calculate their concentration. Okay, you can do that, and use the Ka to find the concentration of hydrogen, and then use it to find the pH. If you have an acid and salt, first you have to find the moles of the salt and use the Ka to find the pH. So I think this is easy. And here is one example, one easy example. Okay, the student plans to prepare a buffer solution that has the pH of 4.50. The buffer solution will contain ethanoic acid and sodium ethanoate. So here you have an acid and salt, right? The student plans to add 9.08 CH3, sodium ethanoate to 250 centimeter cube of 0.800 mole per diameter cube of ethanoic acid. The student assumed that the volume of the solution does not change. So you're asked to show the calculations whether or not the student experimental method would produce the required pH. So in any problem, the first thing you have to do is just read the question more than once, and then you have to write the given information. So this is the info given. You have the pH here. The buffer solution has the pH of 4.50. And the mass, you have the mass of sodium ethanoate, which is 9.08. And you have the volume of ethanoic acid, which is 250 centimeter cube. The concentration of ethanoic acid is 0.800 mole per diameter cube. So this is the given info in that question. Of course, try to read it yourself and just extract these infos and write them aside. Okay, to solve that, you have two ways, as we indicated before. So this is the first way. There's the long way, and there is so much easier way. So this is the first way. You have to calculate. Remember, we said that there are two types of questions, ones that has acid and base, and the other ones have an acid and salt. So in this case, you have an acid and salt. So the first step was to calculate the number of moles for each, right? So the number of moles for sodium ethanoate, easy, and calculate the number of moles for, here you have the concentration and volume. So this is here you have to calculate the concentration, and then you calculate the number of moles. So here you have the number of moles for the salt and the number of moles for the acid, and then you calculate the concentration. Okay, the concentration equals, this is the same rule, Ka equals the concentration of the products divided by the concentration of reactants. Okay, so if we consider the Ka 1.75 times 10 power of minus 5, use that here, just substitute, and you have your answer. This is the pH. Okay, another method, this is the method. Just use the pH. You have the pH, right? Just use it to identify the concentration. And as long as you find the concentration, here you have the concentration of the acid. This was one example. Study it carefully, and I will see you next time. Thank you.